Ever look at like a really complex machine or even just a simple gadget and wonder how in the world does that actually work?
Yeah, like you open something up and it's just gears and wires, and you're like, what is going on here?
Exactly. Well, today we're going to take a deep dive into the foundation of all that, the fundamental principles of mechanical engineering. It's like getting a behind-the-scenes look at how things are designed, built, and yeah, how they actually function.
I love that, a behind the scenes look, because, it's easy to take for granted all the incredible engineering that goes into so much of what we use every single day.
Oh, for sure. Cars, appliances, you name it. This deep dive is all about understanding those fundamental ideas.
And hopefully demystifying them a little bit, right?
Absolutely. Our mission is to really get to the core building blocks, the core principles of mechanical engineering. We're talking materials, how they behave under different forces, all that good stuff. And we want to make sure this is clear, beginner-friendly, not getting bogged down in too much technical jargon.
Yeah, we don't want to lose anybody in the weeds.
Definitely not. And to help us navigate this world, we're using the Mechanical Engineer's Handbook, Materials, and Engineering Mechanics.
It's such a great resource, covers pretty much everything, from the characteristics of different types of materials to the basic laws of physics that govern motion and forces.
It's a wealth of information.
And we're here to distill it down to the essentials.
Exactly. So let's start at, well, I guess the most basic level with the stuff that things are made of, materials. Seems kind of obvious, but what you build something out of is just as important as the design itself, right?
Couldn't agree more. Engineering materials, they're the foundation of everything. And the handbook, really emphasizes this in the preface. Choosing the right material for a specific application, that's crucial.
Yeah, because you could have the most brilliant design, but if the material can't handle the stress or the environment, it's just not going to work.
Exactly, it's going to fall apart.
And one material that just keeps popping up in engineering is steel. But steel's not just steel, right?
Oh, no, not at all. It's way more than just, the plain metal you might picture.
Right, right.
Think of steel as a base. So mostly iron mixed with carbon. But what makes steel really incredible, what gives it so much versatility, are the other things that engineers add in. Alloying elements, we call them. It's almost like cooking, you add different ingredients to get the flavor just right.
Oh, I like that.
So for example, you add chromium to steel, and it becomes much better at resisting rust and corrosion. That's basically the magic behind stainless steel.
So when we talk about stainless steel, that resistance to rust, that's because of the chromium.
Bingo. And that's just the tip of the iceberg when it comes to alloying. Another really important element is molybdenum. Molybdenum helps the steel get harder. It improves its wear resistance, how well it holds up against friction and wear and tear.
Makes sense.
But here's something really important. Molybdenum also helps prevent something called temper embrittlement. So imagine steel becoming unexpectedly brittle at certain temperatures, which is obviously not good.
Yeah, not something you want to find out the hard way.
Exactly. Molybdenum helps prevent that. Plus, it actually strengthens the steel at high temperatures, which is crucial for things like, power plant turbines that operate in extreme heat.
Oh yeah, that makes sense. You don't want a turbine slowly changing shape under all that heat.
Right. And that actually brings us to something called creep, which is like a slow, permanent deformation that can happen to materials under constant stress over time, especially at high temperatures. Not something you want in those critical components.
Definitely not.
Oh,
Okay, so chromium, molybdenum, are there other key elements?
oh yeah. You've got vanadium, which is amazing for making steel hard, especially at high temperatures. That's why you find it in high-speed tool steels, like drill bits that need to stay sharp even when they get super hot. Tungsten also forms really hard compounds within steel, again, really important for those high-speed tools. And then there's aluminum.
Okay, aluminum and steel.
Yep. When you're making steel, aluminum helps to remove oxygen that you don't want. It's a process called deoxidation. And steels treated with aluminum tend to have a finer grain structure, which can be beneficial. And get this, in low-carbon sheet steels used for making things like car body panels, stretching the metal into shape, a process called deep drawing, tiny particles containing aluminum, they actually help to get the right texture. Oh, and in some special steels used in motors and transformers, called electrical steels, aluminum can sometimes even replace silicon.
It's crazy how these small additions can have such a huge impact on how the steel behaves. Now, the handbook also talks about heat treatment. Is that another way to kind of fine-tune the properties of steel?
It absolutely is. It's almost like giving the steel a specialized spa treatment, you know?
Yeah.
You heat it up, you cool it down in controlled ways, and this changes its internal structure, how those tiny crystals within the metal are arranged.
Oh, that's interesting.
So, for instance, if you heat steel and then cool it down really, really quickly, it's called quenching, it becomes incredibly hard, but also quite brittle, kind of like glass.
Ah, okay.
But then you can take that hardened steel and you reheat it to a lower temperature, a process called tempering, and this makes it a bit less hard, but much less likely to just snap. It's like striking that balance between hardness and toughness.
So you're basically making it more usable.
Exactly. And even just the rate at which you cool the steel can result in different internal structures that give you better wear resistance.
So it's about controlling what's happening inside the steel to get the properties you want on the outside.
Yeah.
We've talked about regular steel, but stainless steel is a whole other category, right?
It is. It's like the VIP section of steels.
Yeah.
So stainless steels, they have at least 10.5% chromium, which is what gives them that awesome ability to resist corrosion. That's why they don't rust as easily.
Yeah, you don't see a rusty stainless steel sink very often.
Exactly. But there's actually a whole family of stainless steels, each with slightly different characteristics. You've got your ferritic, martensitic, duplex, and austenitic stainless steels.
Okay, a whole family of stainless steels.
That's right. The ferritic grades, they're often used in, cars and for decorative stuff. Martensitic types, they're stronger and have pretty good corrosion resistance.
Gotcha.
Then you have the duplex stainless steels, which are a mix of, two other types. They're really good at resisting pitting, which is like when little holes form on the surface. And for those super harsh environments like salt water, you even have super duplex grades.
Wow, super duplex, tough name.
Yeah. And the austenitic types, like the really popular 304 and 316, those are super versatile and widely used.
So engineers are basically choosing from this whole buffet of stainless steels depending on what the application calls for.
Exactly. It's all about finding the best fit.
Now, I'm curious, are there any situations where even stainless steel can have problems?
Oh, definitely. Nothing's perfect, right? So, for example, those austenitic stainless steels, while they're generally great at resisting corrosion, they can actually be susceptible to something called stress corrosion cracking.
Okay, stress corrosion cracking, that sounds serious.
Yeah, it's often shortened to SCC. Basically, if they're under stress and exposed to things like chlorides, like in salt water, they can develop cracks. The handbook mentions that this can actually be a real issue in chemical plants using a specific grade of stainless steel, 316L.
Wow, so even stainless steel has its Achilles heel.
It does. But interestingly, you can sometimes get around this. By adding even more nickel and molybdenum to some super austenitic grades, they actually become more resistant to this type of cracking. It's like giving them extra armor.
So tailoring the steel to overcome specific weaknesses, that's pretty cool.
Yeah.
What about welding stainless steel? Is that pretty straightforward?
For the most part, yeah. But with austenitic stainless steels, the main challenge when welding is this tendency to, develop cracks as the weld cools down. They call it hot tearing.
Hot tearing, got it.
Now, for grades with, let's say, less nickel, around 15% or less, you can actually adjust the composition of the weld metal itself to create a little bit of something called ferrite, and that helps prevent the cracking.
Okay.
But for grades with higher nickel content, forming ferrite isn't really an option. So manufacturers, they have to use really pure welding materials to avoid introducing things like phosphorus and sulfur that can actually make that hot tearing even worse.
It's all about understanding the nuances.
Yeah.
Okay, so we've covered steel pretty thoroughly. But steel isn't the only metal in the engineering world, right? What about aluminum alloys? Those seem pretty popular.
Oh yeah, aluminum alloys are definitely big players. They've got some serious advantages. They're super good at conducting both heat and electricity. And if you treat the surface right, aluminum can be an excellent reflector of light. It's actually used in some pretty high-tech applications.
Interesting.
And even though it melts at a lower temperature than steel, it actually takes longer to reach super high temperatures if it's, exposed to a fire.
Oh, I wouldn't have guessed that.
Yeah, it's kind of surprising.
Now, just like with steel, you can mix aluminum with other elements to give it specific properties, right?
Exactly. You can make it stronger or more resistant to corrosion, all sorts of things.
But how do engineers keep track of all these different combinations? There must be a system.
There is. The Aluminum Association, they've got a standardized way of naming all these different wrought alloys. They use a 4-digit number, sometimes with extra letters or numbers tacked on. The first digit actually tells you what the main alloying element is. So for instance, if the first digit is a 2, it means copper is the primary addition. And those alloys, they typically have higher strength.
Oh, that's helpful. So the first digit is like the main ingredient.
Exactly. And the second digit tells you if it's like a modification of the original alloy. So a higher second number means it's a slightly different version, maybe with some tweaked properties.
Got it. So is a code that tells you what's in it.
Exactly. And the handbook actually points out that for specific applications like, say, bearings, where you need materials that can withstand a lot of wear and have low friction, engineers will choose aluminum alloys that have those specific properties. They actually mention an alloy designated 23.0 as having the highest strength among all aluminum casting alloys at high temperatures.
It's amazing how precisely they can tailor the properties for specific applications. Okay, let's move on to another metal we all know. Copper. It's a great conductor of electricity, but what else makes it valuable in engineering?
Copper's got this unique set of properties because of, well, how its atoms are arranged. It's very ductile, which means you can easily stretch it into wires.
Right, we all know about copper wires.
And it's pretty stable chemically. Plus, as you mentioned, it conducts electricity and heat really well. And of course, it's got that distinctive reddish-orange color.
Yeah, you can't mistake copper for anything else. But copper isn't perfect either, right?
Yeah.
The handbook mentions some issues like erosion corrosion and galvanic corrosion.
That's right. Erosion corrosion, it happens when fluids that are moving really fast wear away the protective layer on copper alloys, and it happens faster than that layer can reform. You see this a lot on things like boat propellers and pumps, and if there are any particles in the fluid, it can make things even worse.
Ouch.
And then there's galvanic corrosion, which is when you join two different types of metals together in, an environment where corrosion can occur.
Okay.
The more reactive metal is going to corrode faster. And copper alloys can actually speed up corrosion in aluminum and some steels if they're in direct contact, especially if the copper area is much bigger.
So like a bad neighbor situation for metals?
Yeah, kind of. Conversely, copper itself can corrode if it's touching a more noble metal, like gold or silver.
Fascinating. So how do you prevent this?
The handbook suggests a couple of solutions. You can electrically insulate the metals from each other so they're not in direct contact, or you can use protective coatings to create a barrier.
Gotcha. So you're essentially breaking the circuit, preventing that chemical reaction that causes
Ever
the
look at like a
corrosion.
really complex
Now, what about
machine?
welding copper?
Or even just a
Are
simple
there
gadget
specific
and wonder
techniques
how in
for
the
that?
world does that actually
There are.
work?
Yeah, like you open
Handbook has
something
this
up and
really
it's just
helpful
gears and
table
wires and
that
you're like,
lays out
what
the
is best welding methods for different types of copper and high copper alloys? And it also mentions that you can weld different metals to copper alloys.
Oh, okay.
But you got to be careful because, different metals expand and contract at different rates when you heat them up.
Right. You don't want things warping or cracking.
Exactly. So often they use special welding materials like aluminum bronze or silicon bronze when joining dissimilar metals to copper. They're really good at providing strength and resisting corrosion.
All right. So we've talked about steel, aluminum, copper. What about materials that need to perform in really extreme conditions, like titanium alloys? We always hear about those in the aerospace industry.
Titanium alloys, they're like the rock stars of the material world. They're used in all sorts of demanding applications, especially in aircraft and spacecraft, because, they're super strong but also really lightweight. They have awesome corrosion resistance.
So they're like the superheroes of materials.
You could say that, though they are pretty expensive.
Yeah, there's always a trade-off.
Right. The handbook, it really emphasizes that forging is a key manufacturing process for titanium alloys.
Forging, okay.
Yeah. So it's basically like hammering the metal into shape while it's hot. And this process helps to give the titanium the specific strength and internal structure needed for those critical applications. Improve its tensile strength, creep resistance, fatigue strength, toughness, all that.
So it's not just about shaping it, it's about optimizing its internal structure.
Absolutely.
Forging's like giving it a workout to get it in top shape.
Exactly.
Now, are there situations where you need even more performance than what titanium can offer?
There are. And that's where nickel alloys and superalloys come into play.
Superalloys. Okay, those sound intense.
They are. Nickel alloys are actually a really diverse group. You've got alloys that are great at resisting heat, alloys used for their electrical resistance, stainless steels like we talked about earlier, and then those high-performance superalloys. And the amount of nickel in them can vary a lot.
So it's a broad category.
It is. Some important nickel-copper alloys are Monel, which is used a lot when you're dealing with corrosive chemicals and also in marine environments. And then you have cupronickel, which are also popular for marine applications because they resist fouling.
Fouling, that's like when barnacles and stuff attach themselves to surfaces, right?
Exactly. So you want materials that can handle that in those environments. And nickel alloys, they also do well in environments with things like nitrogen or chlorine. Then you've got your superalloys.
Okay, let's talk superalloys.
So these are alloys based on iron, nickel, or cobalt, and they're designed for super high temperature applications, like in jet engines. They have these really complex internal structures with different phases that give them exceptional strength even when it's incredibly hot.
Wow, sounds complicated.
It is. And manufacturing parts from superalloys, it often involves some specialized techniques like forging, rolling, casting, welding, machining. And it can be pretty tricky to work with them because of their complex composition. Sometimes you even get defects during casting, and then you have to use techniques like hot isostatic pressing or HIP. It's where you apply really high pressure and temperature to fix those defects. Or you might need to do welding repairs.
So it's not just about the material, it's also about the whole manufacturing process to get it right. Okay, let's shift gears completely and talk about something a bit more familiar. Plastics. Or I guess the technical term is polymers.
Right, polymers, they're everywhere these days,
Yeah.
but they behave quite differently from metal.
Oh, yeah, totally different.
The handbook makes it clear that plastics are what we call viscoelastic materials. Basically, it means they have properties of both solids and liquids, kind of. And how they behave depends a lot on things like temperature, the amount of force you apply, the environment they're in, even if they come into contact with certain chemicals.
So it's like they're a bit more sensitive than metals.
You could say that. You can't treat them exactly the same way you treat metals. You have to be more careful with the design and manufacturing process.
That makes sense. So like a plastic ruler will react really differently to being bent or heated compared to a steel ruler.
Exactly. The handbook dives into some examples of different types of thermoplastics, the kind of plastics that can be melted and reshaped. PMP, for example, that's used a lot in medical devices and packaging because it's clear and it doesn't really react with other materials.
Okay.
Then you have polystyrene, which is rigid and a good electrical insulator, but it can be pretty brittle. It breaks easily, and it doesn't do well with solvents. SN, it's similar to polystyrene, but it's a bit better at handling heat and chemicals, but still on the brittle side. PET, that has good strength and toughness and good electrical properties. So you find it in car parts and electrical components. Then there are aromatic polyamides like PPTA and MPIA. These are super strong. They resist chemicals and flames, and they're actually used in things like bulletproof vests.
Wow, bulletproof vests.
Yeah. Then you have PVDF, which is used for electrical insulation and in pipes for handling fluids. And ECTFE, which is known for its high strength and resistance to both chemicals and impacts.
So plastics aren't just for toys and packaging. They have some serious applications. And then there are thermosets, right? Those are different from thermoplastics.
They are. So thermosets like alkyd resins, which are used in paints and electrical components, and dialeaf phthalate, which provides good electrical insulation and can handle high temperatures, they go through this permanent chemical change when they're heated and cured.
So unlike thermoplastics, you can't melt them down and reshape them.
Exactly. They're set.
Got it. And we can't forget elastomers, the stuff we know as rubber.
Right. A common one is Butidi rubber, which is very flexible and wear resistant, but it doesn't like oxygen too much, and it doesn't handle oil very well.
So each type of plastic has its own, personality, its own set of strengths and weaknesses.
That's a good way to put it.
Engineers really have to pick the right one for the job. Now, what about when you want to combine different materials to get even more specialized properties? That's where composite materials come in.
Precisely. Composites are basically engineered materials made by combining two or more different materials to get the best of both worlds.
Okay.
So you've got things like polymer matrix composites or PMCs, where strong fibers are embedded in a plastic, or metal matrix composites, MMCs, where the matrix is a metal, and ceramic matrix composites, CMCs. Carbon fibers, made from pan or pitch, they're often used as reinforcement in composites because they're super strong and stiff. And then there are ceramic matrix composites using things like silicon carbide or alumina as the main body. These can handle really high temperatures, but how they're manufactured really affects their properties.
So by choosing the right reinforcement and the right matrix material, engineers can really get creative with the properties of the composite.
Absolutely. It's like building a material from scratch.
It's like material engineering on a whole other level.
It is. And initially, the main goal was to get amazing strengths and stiffness. But now composites are being used for a lot more than that. They're being used for unique properties like high thermal conductivity so they can move heat really well. Or a low coefficient of thermal expansion, which means they don't change size much when the temperature changes, which is super important in electronics and aerospace. The handbook also points out that if you've got fibers all aligned in one direction, the composite will be really strong in that direction, but weaker in other directions.
Oh, that makes sense.
Yeah. So to get around that, engineers use laminates. It's like layers of composite material with the fibers going in different directions, kind of like plywood.
Oh, that's clever.
Yeah.
So you're basically weaving strength in different directions.
Yeah.
Now, this next category sounds almost futuristic. Smart materials. What are those all about?
Smart materials, they're designed to actually react to changes in their environment in a useful way.
Okay, so they're like materials that can sense and respond.
Exactly. Piezoelectric materials are a great example. When you apply mechanical stress to them, like squeezing them, they generate electricity.
What? That's wild.
And the other way around, if you apply an electric field to them, they'll actually change shape. Quartz, barium titanate, those are some examples. They're used in things like sonar and sensors.
So they're like mechanical electrical converters.
That's a great way to put it.
Pretty cool.
Yeah. Then you have smart polymers. These can change their properties a lot in response to even small changes in their surroundings, like temperature or pH. The handbook talks about the glass transition temperature as a really important concept with polymers. It's the temperature where they can go from being hard and brittle like glass to being soft and rubbery. And things like their volume and stiffness can change dramatically around this temperature. So engineers have to be very aware of that.
So they can almost switch personalities depending on the temperature. Now, we've talked about metals, we've talked about polymers, but what about ceramics? Those seem like a totally different beast.
They are. The handbook emphasizes that with ceramics, even more so than with metals, how they're manufactured really dictates their properties. And a key characteristic of ceramics is that they tend to be brittle.
Brittle.
Yeah. Unlike metals, they don't bend or deform much before they just break. And another thing, the strength of ceramics can vary a lot because of tiny imperfections or flaws within the material. And to describe this variation in strength, they often use something called the Weibull distribution. It's a statistical tool.
So instead of saying this ceramic has this specific strength, it's more like it has this probability of failing at a certain stress.
That's a good way to think about it.
It's all about probability.
Yeah. But even though they can be brittle, ceramics have found all sorts of crucial applications.
Oh, yeah. Like what?
Well, in cars, they're used in parts that experience a lot of wear, like rocker arm inserts and tappets.
Okay.
And in medicine, their wear resistance and the fact that they don't react badly with the body, their biocompatibility, makes them suitable for things like hip and knee replacements.
Oh, wow. That's incredible.
Yeah. And they're great in high-temperature applications, like in turbochargers and some parts of jet engines. And in electronics, ceramics are essential for insulation, capacitors, and as substrates, which is like the base material for circuits. And in those applications, their ability to conduct heat and how much they expand or contract with temperature changes, those are critical properties.
So it seems like every type of material has its own challenges and advantages. Engineers have really learned to work with them all. Now, the handbook also briefly mentions something called surface engineering and treatments. What's the point of those?
Surface engineering is all about modifying just the outer layer of a material to improve its properties without changing the whole material itself.
Okay, so it's like giving it a special coating or treatment.
Exactly. This can be treatments to prevent corrosion, like chromate conversion coating or anodizing aluminum, or treatments to help coatings stick better. Encapsulation, also known as potting, is another type of surface treatment where you basically embed electronic components in a protective material. It makes them more rugged, protects them from the environment, provides electrical insulation, and helps with heat dissipation.
Okay.
And, of course, printed circuit boards or PCBs, which are like the foundation of most electronic devices, they're made from specific materials like FR4 glass epoxy.
So it's all about optimizing that interface between the material and its surroundings. Now, all this talk about materials and forces, it brings us to an important topic, which is making sure things are reliable, that they don't just break unexpectedly.
Reliability is key. And in mechanical engineering, vibration and shock, Those are big concerns. Vibration, which is basically that back and forth motion, it can cause a lot of damage if parts of a machine start vibrating excessively at their natural frequency. It's called resonance. And that can lead to, cracks, fatigue in the metal, parts coming loose, all sorts of problems.
Right.
Shock is like a sudden, intense force that can also cause damage. The handbook briefly talks about ways to isolate equipment from shock and vibration, basically trying to cushion or dampen those forces.
So you're trying to either absorb that energy or redirect it somehow.
That's the idea.
Now, with so many different materials and properties to consider, how do engineers even start to choose the right one for a particular application? It seems overwhelming.
It can be. That's why having reliable materials data and a good selection process is so important. The handbook stresses the need for good data about the material's properties, things like strength, stiffness, how it behaves at different temperatures, all that. And you can find this information in handbooks and also in electronic databases from organizations like ASM International and Novel. But here's the thing. The data is only really useful if you know how it was obtained, the testing conditions, how much variation there might be, how the material was processed.
So it's not just about the numbers, it's about the context.
Exactly. That background information is called metadata, and it's super important.
Gotcha. So what's a general approach to actually picking a material?
The handbook outlines a basic process. You start by defining what absolutely has to be met. The performance requirements, the must-haves, these are called rigid properties. You use those to eliminate materials that are just not going to work. Then, for the materials that are still in the running, you develop a rough idea of what the part will look like, how it will be shaped. Finally, you consider the nice-to-haves, the soft requirements, things that would be great but aren't absolutely essential. And then you use kind of a logical approach to compare and rank the different options, taking into account how important each of those soft requirements is.
So it's like a process of elimination, narrowing it down based on what's essential, and then fine-tuning based on the desirables.
That's a good way to put it.
Now, we've spent a lot of time on materials, which are obviously super important. But the other key part of mechanical engineering is, well, the mechanics. How do things behave when forces act on them?
Right. Now we're getting into the nuts and bolts of engineering mechanics. And it all starts with the basic ideas of stress and strain. Stress is basically how much internal force a material is experiencing per unit area. It's a response to an external load.
Okay, stress, got it.
So you've got tensile stress, which is when you're pulling on something, like stretching it.
Okay.
Compressive stress, which is when you're pushing on something, squishing it. And shear stress, which is when you're trying to slide one part of the material past another, like when you're cutting something with scissors.
I can visualize that.
The handbook even has some diagrams that show these different types of stress, which can be really helpful.
Oh, that's nice.
Strain, on the other hand, is how much the material deforms as a result of that stress. So it's measured as like the change in length relative to its original length.
So stress is like the internal resistance, and strain is the resulting change in shape.
That's a good way to think about it.
Okay, so what about when you have something like a beam, a long structural element? How are those stresses and strains distributed?
That's a great question. So, when a beam bends, it experiences what we call flexural stress, which is highest at the top and bottom surfaces of the bend. And there's this formula, it's called the flexure formula, that relates the bending force or bending moment to the stress and the shape of the beam.
Okay.
And there's this interesting concept of a beam of uniform strength, where the shape of the beam actually changes along its length so that the maximum stress is the same everywhere.
Well, that's interesting.
Yeah. It's a cool idea, but it's often not really practical to manufacture. Then you have situations where a beam might rest on more than two supports. It's called a continuous beam.
Okay.
And those are a bit more complicated to analyze because you have to figure out how the bending forces are distributed before you can even determine the reactions at the supports.
So more supports, more complexity. Now, what happens if the force isn't applied gradually, but it's more of a sudden impact?
When a load is applied suddenly, that's called impact loading, and it can create much higher stresses and strains in the material compared to, if you applied that same load slowly.
Makes sense.
So if you drop a weight onto a bar, for example, that energy from the impact is absorbed by the bar, causing it to deform and experience stress. The handbook provides equations to help you analyze this kind of axial impact, taking into account things like how high the weight is dropped, how heavy it is.
And that's got to be important for designing things that might experience sudden impacts.
Yeah.
Now, another type of force is torsion, right? That's when you're twisting something.
Exactly. Torsion happens when a shaft, or a similar component is subjected to a twisting force. And the handbook provides formulas for calculating the stresses and strains in those situations, both for solid round shafts and even for hollow tubes.
Okay.
And generally, when a shaft fails due to torsion, it's the outermost parts that experience the highest stress, so they're usually the first to go.
Makes sense. What about when you have, say, a long, slender column and you push on it? It might not just compress, it could also buckle, right?
You got it.
Hmm.
Buckling is this instability that happens when a long, thin column under a compressive load suddenly bends or bows out sideways.
Okay, so it kind of gives way.
Yeah. And how likely it is to buckle depends on a few things. How long and slender it is, the shape of its cross-section, what material it's made of, even